Right now, at this exact second, a woman is standing on a train platform in Hong Kong checking her phone, completely unaware that 30 meters above her head, a 200,000-ton container ship is gliding silently across Victoria Harbour. And she has no idea that the only thing separating her from the entire weight of the ocean is a wall of concrete less than the length of a school bus, thick. And somewhere in a control room, an engineer is staring at a sensor reading that has been creeping upward, 0.4 millimeters a day, for 6 straight weeks. And nobody can explain why, and if that number crosses one more threshold, they will have to shut down a railway that 500,000 people depend on every single morning. And this is the story of how that number got there, and what it took to build the tunnel underneath it. For 43 years, Hong Kong had a wound that never healed. A train line called East Rail ran right up to the edge of Victoria Harbour and simply stopped, like someone had drawn the tracks on a map and then forgotten to finish the sentence. On the other side of that, water sat 500,000 commuters every morning, cut off from the beating financial heart of the city, forced into overcrowded ferries and buses that turned a 15-minute trip into an hour of gridlock. Engineers had looked at solving this for decades. Every single time, they hit the same wall, the harbour itself. Not politically, not financially, physically. Because underneath Victoria Harbour, in water that looks calm and empty from the surface, there are already 5 tunnels crossing back and forth. Road tunnels, rail tunnels, a tangle of concrete, arteries that Hong Kong had been threading beneath its own harbour bed for half a century. To connect East Rail to the rest of the network, engineers would need to build a 6th tunnel and somehow slide it through a gap in that tangle only 90 meters wide, in water 400 meters across, without touching a single one of the tunnels already down there, without interrupting one of the busiest shipping lanes on the planet, and without anyone above the surface ever noticing it happened. This is the story of that tunnel. And it is not a clean story. It is a story where the ground itself tried to stop them, where a piece of the past 900 years old rose up out of the mud to change the entire design, where a hidden mistake almost forced them to tear out a wall holding up a live railway station, and where, even after the trains started running, the harbour was still testing them, one silent millimeter at a time. It starts, of all places, in a quarry. Miles from the water, engineers built an enormous dry basin, sealed off from the sea by a single retaining wall, and inside that basin they began casting 11 individual concrete boxes. Not small boxes. Each one 23,000 tons. Each one large enough to swallow a train whole, with room to spare, and every single one of them had to be built to a tolerance so tight it sounds almost absurd. 5 millimeters of flatness across a casting bed, 160 meters long. When the crews first measured that bed, it was out of level by 340 millimeters, 68 times the allowable error. If they had poured concrete onto that surface as it was, the finished tunnel elements would never have lined up on the harbor floor, and the entire alignment of the crossing would have been thrown off before a single element ever touched water. So they went back with grout, filling every low point by hand, checking, rechecking, filling. Again, until that entire football field length surface came in under 5 millimeters, flat enough that you could have played billiards on wet concrete. Only then could the real pour begin, and when it did not stop. 36 hours of continuous concrete pouring per section, no pauses, because a modern high-strength concrete mix like this generates its own heat as it cures, and if the pour stops even briefly, you get what engineers call a cold joint, an invisible seam of weakness buried inside a wall that is supposed to hold back an ocean. Thermal sensors were buried inside the walls themselves, tracking the internal temperature in real time, because if that curing concrete got too hot too fast, the whole element could crack from the inside before anyone even knew something had gone wrong. And inside those walls, workers were physically climbing through a cage of steel reinforcement so dense that in places, a human being had to twist sideways just to fit through the gaps between the bars. 23,000 tons of steel per section, wrapped through concrete forms with an inspector checking every single tie point, because every tendon and every anchor plate inside that structure would eventually be holding back 30 meters of harbor water. And there is no such thing as an acceptable margin of error when the alternative is a flooded tunnel full of passengers. It took 30 months just to cast all 11 sections. Then came the part. Nobody could rehearse, getting them into the water. The wall separating the dry casting basin from the open sea came down, the harbor rushed in, and 11 concrete boxes that had spent months sitting on dry land began impossibly to float. 23,000 tons of steel and concrete, buoyant, rising off the ground they were built on, tracked to the centimeter by GPS towers mounted on their own roofs. Because from this point forward, every single movement of these structures had to be known, logged, and controlled. And then, at night, under cover of darkness, they moved these things into one of the busiest stretches of open water in the world. Picture it, a 200-meter wide shipping lane, container ships and tankers moving through it around the clock, and gliding into that same lane, an object the length of a football field and the weight of a small mountain, moving at walking pace, escorted by 5 tugboats with marine police physically shutting down 200 meters of live shipping channel for every single crossing, 48 hours per element, 11 times, each one a fresh negotiation with one of the busiest ports on Earth. Before any element could touch the seabed, that seabed had to be prepared with a precision that borders on obsessive. Dredgers cut a trench 30 meters into the harbor floor, and the base of that trench had to be accurate to within 100 millimeters, because if that trench floor was uneven, a 23,000-ton concrete box would settle unevenly on top of it and could tilt permanently, locking a fault into the tunnel forever. On top of that trench, divers and machines laid a bed of gravel, screeded flat underwater using lasers, accurate to 20 millimeters across the entire footprint of the element, 20 millimeters underwater in a tidal harbor, supporting a structure heavier than the Eiffel Tower. And then, on the night each element was ready, giant pontoons gripped it from above, ballast tanks slowly filled with water, and inch by inch this enormous structure began its descent into the dark, 30 meters down. And this is where the harbor showed them, for the first time, exactly how little control they actually had. During one of the descents, engineers discovered that a cargo ship's anchor had dragged across the prepared seabed at some point before the operation, disturbing the carefully leveled gravel bed by 180 millimeters, 9 times the allowable tolerance. The element they were lowering, 23,000 tons of concrete already partway into its descent, could not be allowed to land on a damaged foundation. So they stopped. They held that impossible weight suspended 15 meters down in the harbor while divers went back in, re-screeded the bed by hand, and reconfirmed the 20-millimeter tolerance before the descent was allowed to continue. And the engineer who oversaw that operation later called it the moment that nearly broke the entire team, because for those hours, holding 23,000 tons in the water column with nowhere to put it, there was no plan B. When each element finally touched down, the joint between it and the previous one had to be sealed instantly. A specialized rubber gasket called a Gina seal, compressed between 2 23,000-ton concrete faces by the sheer hydrostatic pressure of the harbor pushing them together, millions of tons of natural force doing the work no machine could. Once that connection held, the water trapped between the 2 elements was pumped out, and a second seal was installed from the dry side inside the tunnel itself, meaning that by the time it was finished, there were 2 separate independent barriers standing between every future passenger and the entire weight of Victoria Harbor. Do that 11 times, at night, 1 element at a time, over years, and you have crossed the harbor. But the harbor was never the only obstacle. On land, 7 massive tunnel boring machines were chewing through the rock and reclaimed soil beneath the city in 4 separate drives, and every single one of them was cutting through completely different ground, because Hong Kong's geology beneath the surface is not one continuous. These machines operated on pressurized slurry, essentially drilling inside a controlled bubble of fluid pressure calculated to hold the tunnel face stable, sometimes with less than 3 meters of solid ground between the cutter head and the harbor above. 400 old timber and concrete building piles from structures built decades earlier sat directly in the planned path of the tunnel, forcing engineers into an impossible choice: break straight through them or reroute an entire tunnel drive around obstacles nobody had fully mapped. And behind the cutter head, a lining ring of concrete segments had to be installed before the machine advanced even 1 more meter, because without that ring locking the tunnel open immediately, the ground above would simply collapse into the void the machine had just carved. Then, 400 meters into one drive, the machine simply stopped, dead. An uncharted mass of old concrete, a forgotten foundation raft from a structure nobody had records for, had jammed the cutter head completely. Engineers had to drill probe holes from street level down to the obstruction to confirm exactly what they were dealing with, then grout and stabilize the area before the machine could resume, losing 8 days on a schedule that had no slack to give. Where tunneling couldn't happen mechanically, it happened with explosives, blasting through live Hong Kong granite meters beneath 50-year-old apartment buildings still occupied by families going about their evening. Every single blast calculated down to the gram of explosive charge to keep vibration below the threshold that could crack plaster on a wall 10 stories up. 200 sensors were mounted on the buildings directly above the theater, blast zones, and the rule was absolute: 1 single reading over the safety limit, any time, day or night, and blasting stopped immediately. No exceptions, no negotiation, no matter how far behind schedule the project already was. In one section, engineers had to excavate a 300-meter station box with 50-year-old residential towers pressing in from all 4 sides. held back only by deep diaphragm walls plunged into the earth before excavation even began. All the walls that had to hold, because there was no room for error with families sleeping directly above an open pit. And then, in the middle of digging that very station box, workers hit something nobody expected. The remains of a settlement over 900 years old, dating back to the Song dynasty, complete with ancient wells still intact in the soil. Construction stopped entirely. Archaeological teams moved in. 11 months disappeared from the schedule, and the financial cost of that discovery alone ran into the billions. But the truly staggering part came next. Rather than simply removing the historical site, engineers made the decision to redesign the entire station around it, physically shifting the structural grid 3 meters sideways to preserve wells that had been sitting quietly in the ground since before Hong Kong existed as a city at all. History won that argument, and the schedule simply had to absorb the loss. Elsewhere, the ground itself refused to cooperate in a different way. Soil beneath one exhibition center was found to still be settling from reclamation work done years earlier, forcing crews to inject and stabilize the soil before they could dig anywhere near it. And even with that precaution, 3 separate buildings in the area began sinking faster than predicted, triggering emergency underpinning operations where teams worked through the night to physically hold the structures in place while the ground beneath them was reinforced. 6 meters above one tunnel boring machine, cars were driving across Harcourt Road with absolutely no idea that a slurry pressurized machine the size of a building was threading beneath them in that exact moment. And by this point in the project, you might think the greatest danger had already passed, that the geology had been beaten. It hadn't. The next crisis wasn't underground at all. It was human. During a routine inspection deep inside one of the diaphragm walls forming part of a live operating station, an inspector found something that should never exist in a structure like this: a rebar coupler that wasn't connected. In a wall like this, steel reinforcing bars are supposed to be joined end to end using mechanical couplers, creating one continuous chain of steel. Strength running the full height and length of the wall, a wall that isn't just holding back excavated earth during construction, but is designed to permanently carry the load of a live railway station for the rest of its operational life. That one disconnected coupler wasn't an isolated mistake. When the investigation widened, engineers found 1,900 more, short lengths of rebar that had never been properly connected, simply dropped into the wet concrete during the original pour and buried inside a wall that was, by that point, already holding up trains running above it every day. Nearly 9% of the entire connection system in that wall was missing, and the wall was structurally live the entire time this was discovered. The response was immediate and total. The operator halted all new concrete pours across the entire project, and every single diaphragm wall built by that construction team came under independent investigation. But you cannot simply chip open a wall that's holding up a functioning train station and hope for the best. So instead, engineers designed an entirely new steel support structure to bypass the compromised sections completely. A frame engineered to intercept the loads from the trains above and carry them safely around the defective concrete rather than through it. Installing that fix meant removing 650,000 tons of rock beneath a station that could not stop running, not even for a single day, which meant the work only happened in the narrow window after the last train of the night and before the first train of the morning. Engineers describing nights where the final train passed just 45 minutes before an entire zone of rock had to be cleared to make room for the next phase of the fix. 5,000 tons of steel were welded together underground, in a confined remedial space with no crane access and no sky above, heat and sparks in total enclosure, assembling a structure strong enough to quietly take over the job the original wall had failed to do. When the independent inquiry finally confirmed the fix was structurally sound, work resumed, but 4 years had been lost to a mistake buried inside concrete that no one could see from the outside. And the project moved on to a stretch of tunneling that would turn out to be even more dangerous than anything that came before it, because this time the danger was directly beneath one of the busiest live railway platforms on the entire island, carrying 10,000 passengers every single hour, while, at that exact moment, workers below were drilling into solid rock only meters beneath the rail bed of a 40-year-old operating tunnel line, running trains every 3 minutes with absolutely no interruption to service. As the excavation progressed, monitoring sensors picked up something alarming. The existing tunnel above was moving, settling downward, 22 millimeters, 2 millimeters past the maximum allowable limit. Every operation below that section stopped immediately. Standing in that space, engineers described being able to physically hear the trains rumbling directly overhead and watch dust shake loose from the ceiling with every passage, a visceral, immediate reminder that this wasn't an abstract number on a monitoring screen. It was a live railway line sinking in real time above their heads. Working in a space too tight and too dangerous for any crane, crews hand-tightened steel support props beneath the moving tunnel, racing to install enough structural support to arrest the settlement before it crossed into territory that could force a full closure of one of Hong Kong Island's busiest lines. Overnight recalculations bought them a narrow safety margin, and the settlement finally froze at 23 millimeters, 1 millimeter from where engineers privately believed they would have had no choice but to shut the line down entirely. 650,000 tons of granite were excavated from beneath that station at night, every single night, so that by sunrise, the platforms were clear and ordinary commuters walked across floors that had, hours earlier, been an active excavation zone 1 level below their feet. The station effectively grew downward one slab at a time, each new level cast beneath an existing one while passengers walked overhead completely unaware, and 5,000 tons of steel were assembled underground, lowered through a construction shaft in sections small enough to fit, because there was no way to lower a crane and no sky to lower anything from, into a job site buried this deep beneath a living city. Even the engineering of the harbor crossing itself carried a problem unique to connecting a floating structure to a fixed one. The immersed tunnel sitting on the harbor floor moves up to 30 millimeters with every single tidal cycle, expanding and contracting with the rhythm of the ocean above it, while the bored tunnel connecting to it on land is completely rigid, fixed in solid rock, incapable of moving at all. The joint between these two fundamentally different structures had to somehow flex 30 millimeters, twice a day, every day, for the next 100 years, while still holding back 3 atmospheres of water pressure, and the standard rubber seal used in tunnel joints worldwide simply wasn't rated for that kind of a repeated movement over that kind of time scale. So engineers designed something new, a custom Omega Profile seal, tested in laboratory conditions at 2.5 times its expected operating pressure, engineered from scratch to survive 30 millimeters of daily flex for a full century, effectively creating a new engineering standard because the existing one wasn't good enough for what Hong Kong Harbor demanded. Deep beneath one of the busiest intersections in the city, station levels were excavated 25 meters into land that had itself been reclaimed from the sea and was, decades later, still settling under its own weight, meaning the diaphragm walls holding back that excavation were the only thing, standing between an open pit and land that hadn't fully finished moving. 4 separate rail lines were made to converge at 4 different depths in a single interchange, stacked so precisely that the lowest platform sat directly beneath a live 40-year-old tunnel with, by design, 0 physical contact between the two structures, despite being separated by mere meters of engineered ground. At one point, a tunnel boring machine passed just 6 meters beneath a live city street while monitoring instruments above recorded 8 millimeters of ground movement, while within limits, but only barely, with 3 separate operating rail lines running above a single excavation for the very first time anywhere in the project's history. A feat of coordination that had simply never been attempted at this scale before. And then, after a decade of blasted granite, flooded near misses, buried mistakes, ancient wells, and midnight tunneling beneath the busiest transit corridor in Asia, the physical construction was finished. Concrete poured, steel welded, tunnels sealed, but none of it, not one single system, had actually been switched on yet. The tunnel had been sitting quietly on the harbor floor for over a year by the time track lane crews arrived to install the rails that trains would eventually run on, and every single one of those trains would depend entirely on an automated signaling system to know where every other train on the network was, in real time, at every second. A system where failure doesn't mean a delay. It means no train moves anywhere on the line, not one, ever, until the fault is cleared. That signaling system took 8 months of reconfiguration to certify, and in the process of getting it right, engineers uncovered a separate, unrelated problem: the platform's screen doors installed to protect passengers from the track edge and the trains themselves weren't communicating correctly, a discovery that added an entirely new layer of testing onto a system already under intense scrutiny. Electrical crews energized the full 27.5 kilovolt system running through 5 kilometers of tunnel and held it live for 72 straight hours, hunting for any fault at all, however small, before a single passenger would ever be allowed near it. For 12 full months after that, empty trains ran the entire route daily, stress testing every mechanical and electrical system under real operating conditions, catching failures in a controlled environment before they could ever have the chance to happen with a single paying passenger on board. Beneath the harbor itself, 23 separate groundwater sensors were installed to watch the seals continuously, with a standing rule that any reading rising above its established baseline would trigger a physical diver inspection within 24 hours. No exceptions. One engineer, describing what it feels like to stand in that tunnel as a train passes overhead at 90 kilometers an hour, said that with the vibration dampers installed, he feels absolutely nothing. But without them, the movement is 4 millimeters, enough to feel through the concrete beneath his own feet. And then, quietly, almost Invisibly, 2 of those 23 groundwater sensors, numbers 7 and 8, began rising. Not dramatically, just zero point 0.4 millimeters a day, day after day, creeping toward the half-millimeter limit that would trigger an emergency dive inspection of a seal sitting 30 meters beneath one of the busiest harbors on Earth. The seal, as far as every instrument could tell, was completely intact, but something down there was still moving, millimeter by millimeter, and nobody could say with total certainty why. 347 separate open items were eventually closed out. The Independent? Inspectorate finally signed off. The tunnel was certified, opened, and today carries hundreds of thousands of commuters beneath Victoria Harbor every single day, cutting a journey that once took the better part of an hour down to a matter of minutes. But engineers didn't stop watching. They ran storm surge simulations with over 2 million individual structural elements modeled against worst-case flooding scenarios, sitting in front of screens in total silence, as the software modeled forces the tunnel would only ever face once in a generation, if it was unlucky. And somewhere above all of that, right now, as you're hearing this, a container ship is crossing Victoria Harbor, and the wash from its propellers is pressing down ever so slightly, compressing the Gina seals sitting on the harbor floor 30 meters below its hull, a rubber gasket holding back an ocean, flexing under the weight of a ship whose captain has absolutely no idea it's happening. So that somewhere beneath him, in a train carriage full of people checking their phones and thinking about dinner, absolutely nobody feels a thing.